Hi and welcome. I'm Mike Carey. I'm a consulting architect for Couchbase, working on Couchbase Analytics and the Couchbase Columnar cloud offering, which I'm going to tell you about today. I'm also a retired faculty member, spent a number of years teaching database technologies to students at UC Irvine and before that, University of Wisconsin-Madison. And so I'm going to give you kind of a database guy's view of Capella Columnar, talking about both its functionalities and what's interesting, and also like what's under the hood. So what are the technologies that enable those functionalities and what's interesting and unique about those? So hopefully, if you're a sort of a engineering oriented or interested in how things work and what Columnar does, you will enjoy this talk. Let's get started. Welcome. My goal in this next roughly an hour or so is to give you an overview of a new cloud database as a service offering from Couchbase called Capella Columnar. And what I want to do is to talk to you about sort of two aspects of it. One is like, what is it? You might make some assumptions about it based on its name. And I want to just sort of cover the full functionality that it provides. And I also want to talk about kind of the cool stuff under the hood. So this is really sort of an engineer's perspective on Capella Columnar and what's under it and why it should be interesting. Okay, so what I'm going to do, I'm going to take you through a few things here. First of all, I'm just going to explain the kind of data that Columnar is designed to deal with. JSON, it's not a relational engine, and why that's important, what's interesting about that. Talk about the capabilities of Capella Columnar as a system, as a cloud offering, and then talk about the stuff under the hood, just to give you a sense of the range of things that are involved in delivering its capabilities. And then I'll wrap things up and show you a little screenshot at the end. All right, so first of all, let's talk about the kind of data that Capella Columnar is all about. So it's about JSON. JSON stands for JavaScript Object Notation. In a nutshell, it's a lightweight format. It's a textual format so that both people can read it and machines can read it. JSON objects are built up of primitive types and records and arrays, and you'll see some examples in the course of the talk. It is widely used. You're probably all familiar with it, actually, but just to review, for data exchange, for web applications, so it's gotten very popular, and it's really the format of choice for AI-infused applications and remote service calls and things like that. And so one of the things that makes it interesting is that it's pretty general in terms of the kinds of data that it can sort of be viewed as modeling. So JSON data can actually be a way of seeing relational tables, NoSQL document collections in your favorite NoSQL databases, CSV, TSV files, Parquet files. They can all be sort of seen if you put on JSON glasses by looking at what it would look like in JSON. And then applications use this very commonly, and so you could sort of, think about a JSON object for a shopping cart. And so what we're going to do with Capella Columnar is sort of put on JSON glasses and sort of see all this different kinds of data that way, and I'll explain that more as we go on. So what is Capella Columnar? You can think of it as sort of being sort of a JSON operational data warehouse, if you will. So one of the questions you might ask, given that description, is, why shouldn't I just use a relational data warehouse or a data lake? And the relational answer is that the model has served us well for 5 decades, right? So it's 2024. Relational model was brought to us by Ted Codd in 1970. So it's been a while, right? So the relational model has served us very well for doing data management for 5+ decades. It gives us simple querying thanks to SQL. It also gives us when we teach about SQL, my previous life, I was a full-time professor teaching SQL to thousands of kids. And so one of the most important things about it is SQL gives you data independence. It allows you to see your data as tables. And tables with links that are based on data values, as opposed to thinking about it as a bunch of objects wired together with pointers, right? So it gives you this very nice high-level view and a language for talking about your data and asking questions about your data in that high-level language. There have been decades of research on how do we process SQL queries well, how do we parallelize the execution of SQL queries so that we can do queries over very large volumes of data. But it's not the end all. So relational databases require your data to be flat. They require your data to have a rigid schema. So you have to know up front, like what are all the fields your data is going to have and what are the data types of all those fields. And if things change, that becomes challenging. So it's sort of rigid. It's a brittle thing where it's hard to keep your applications and your databases in sync and to scale things out in the way you want in terms of upgrading things and so on in a rigid world like that. And the answer that relational databases have come up with for dealing with JSON data, which is becoming quite prevalent today, is okay, we've got integers and strings and, we've got other kinds of data types. We'll just make another kind of data type called JSON and we'll stick our JSON data in there. So the answer in relational databases is to basically bolt on JSON as another column type. Capella Columnar says that's like not the thing to do, but rather let's bring those 5+ decades of knowledge to bear on dealing with flexible JSON data. And as a result, to come up with a really nice platform for doing JSON analytics. So the way we do that is SQL++ is an extension of SQL for JSON. And that kind of gives you the JSON glasses with which to see your data. JSON as a data model means that, if you have JSON in your application, you can now bring it into your analytical platform and deal with it as JSON. So you don't have to ETL your data and flatten it and know all the data types and et cetera, and then deal with the change lifecycle. And the analysis that Capella Columnar allows you to do, as we'll see, allows you to kind of mix static and dynamic data collections and data coming from various places. And again, I'll sort of make that clear as we go on. So what are the key features of Capella Columnar? So some of you watching this video may be familiar with a previous generation of our technology called Couchbase Analytics, which allowed you to do JSON analytics for data in the Couchbase platform, Couchbase Capella, and the on-prem offering. What Capella Columnar brings is the language SQL++, SQL for JSON, a scalable MPP-based, like partition parallelism-based query evaluator for SQL++. And now we have native columnar storage for JSON analytics, and I'll explain what that means. That columns and JSON might sound funny together, but I'll clarify what that means. It also provides compute storage separation, so you can have your data sort of stored, and you can fire up your compute on top of that data. Cost-based query optimization for SQL++ over this data stored in the Columnar service. The capabilities for doing continuous ingestion of data from elsewhere, from other Couchbase, from your operational Couchbase and up in Capella or your on-prem Couchbase via DCP, we'll talk more about that, or from your other favorite data sources and important data sources in your enterprise via Kafka, and we'll also talk more about that. And then the Capella Columnar also provides new optimized access to external storage. So if you have data sitting in S3 or one of your favorite object stores, you can get access to that data. And we have some optimizations for that we'll be talking about. And then finally, sort of increased business intelligence tool integration. Okay. And so basically, this is not Couchbase Analytics rewarmed. This is a new thing. And everything you're seeing in red here is new in Capella Columnar. So these are all new features that you get when you use the Capella Columnar service. And of course, it's in the cloud. All right, so if we were to sort of put together what you might call an architecture diagram, a marketing architecture for Capella Columnar, what you see is the Columnar service here in the middle with sort of the JSON database engine. Under it are support for columnar storage, MPP for query execution, SQL++ as the language, so the SQL++ compiler, the dealing of the JSON data, and a cost-based optimizer, all on top of, logically speaking, storage compute separation with S3 storage kind of at the bottom here. And actually, we're sort of moving this also over time to other storage. Google, for example, is coming soon. So now, on the left-hand side, what I'm showing you are places where data might come from to be held in Capella Columnar and analyzed in Capella Columnar. So basically sort of Couchbase on-prem or Couchbase Capella operational data can be one of the things that feeds into your data collection in the Capella Columnar platform. You can get data from relational databases, from MongoDB today. DynamoDB is coming very soon. Sort of Cassandra's on the horizon. And then you can also deal with external data or access external data in object stores, for example, S3, but we support sort of access to other object stores as well. So JSON, TSV, CSV, Parquet formats. On the right-hand side in this sort of architecture picture are the various ways that you can talk to your data. So we support access from BI tools, and we'll talk more about that, like Power BI and Tableau, and more coming soon. We have an SDK for an application to talk to Columnar, data APIs, Capella user interface. We'll show you a little picture of that at the end. And then something called Intelligent Query, which is also fun. And I'll talk a little bit about that at the end as well. All right. So that's in a nutshell what Capella Columnar is when you look at it from outside. What's under the hood? Like, why is Capella Columnar something that is interesting under the hood? So let me start by sort of positioning how we see it fitting into the IT universe. So this is kind of a rough conception, engineer's conception of how enterprise IT and Capella Columnar fit together. And maybe the main point to take away is that this is a place, Capella Columnar is a place where, it's a casual place to put your data. Data can come as it is. So today, let's suppose you have a universe where you've got some applications like a shopping application feeding into operational databases, and maybe it's, Couchbase. Maybe you've got a call center that's feeding data into another operational database. Maybe it's also Couchbase. Maybe you're scraping social media looking for, what are people saying about your products, and you're scraping that into maybe, the team that built that, made a different buying decision, and so that's in somebody else's NoSQL database. And then maybe at HQ, you've got your, traditional relational database, that's been there for 30 years powering things. So you've got data in a relational database. And so now you've got a bunch of analysts, right? Their jobs are, or data scientists for that matter, who are trying to put together, sort of insights from that data. And so sort of in the world today, they're maybe, if it's more traditional enterprise, they're feeding this data into a data warehouse. And remember that those are based on the relational model. And so there's flat requirement for your data, right? So there's this extract, transform, and load, or ETL for short, process that needs to move data from these different sources into the data warehouse. Or, if you're a more modern enterprise, then maybe, you're depositing raw data into a data lake and analyzing data kind of just in time, but maybe ETLing some of that data from your data lake into your data warehouse. And then you've got your BI tools and your data science tools kind of talking to your data wherever it is. And so the analysts are basically, waiting to analyze that data. And so those ETL processes have to run when something changes, right? So somebody puts some new feature in the shopping app and there's some new, sort of fields in that application. Then there's also a whole change process that needs to happen to, update the databases and the app, but then also figure out how that new stuff should be reflected in the data warehouse or the data lake, and how the ETLs have to change and so on. So the analysts are over here wanting to provide insights to the company, right, and make the user experiences better, et cetera, based on those insights. And they are waiting for that data, but they don't necessarily have to wait, right? So if you use Capella Columnar, our vision for you is that a lot of those analysts that used to be sitting here on the far side of the data lake or the far side of the warehouse, sort of waiting for the data to show up, can do their analysis essentially immediately. And the data, can still be going into a warehouse, can still be going into a data lake, but much more can be done on the data as it is right now. So what do I mean by that? Well, so if you have your applications, feeding your operational databases, you've got your call center, you've got your, sort of your scraping of social media, all those things can deposit their data in the form that it is, JSON data, into Capella Columnar. And that data can be, as we'll see, sort of continuously fed from these sources into Capella Columnar, including relational sources. And a lot of the insights which need access to this data can be obtained without waiting for the whole warehouse process and sitting on the far side of the warehouse and the far side of the lake waiting for data to come. So sure, there's some analyses that really might need to sort of wait till all that data is settled in that form, but much of the questions can be now answered sort of quickly on that data. This is, this data as it is now, as opposed to as it is, at midnight when the data gets moved, or 2 months from now when the ETL process gets updated to accommodate the new fields. So this is kind of how Capella Columnar fits in. We're not saying no warehouse or no data lake, but there's an awful lot of analysis that you can do on your sort of operational data and answer questions. So when you launch a new product, you can watch how things are going. You can see when the call center lights up, when something's going wrong, and what people are saying in social media if something's going wrong, and react to that, get a sense of how things are. Immediate feedback, sort of shortening that time to insight. So that's the vision for how Capella Columnar would sit in, sort of a typical enterprise. All right, so let's now go through the features that Capella Columnar offers, and we'll sort of go outside in. So in that picture, you saw BI tools being able to do analysis. And those BI tools, let me go back to this picture, those BI tools can be talking to Capella Columnar and getting these immediate insights. Okay, and so this we have a way of enabling relational BI tools to kind of look at that JSON data and as though it were relational, and extract those insights from that data as it's sitting in your Columnar service. So we have support today for Tableau and Power BI, again, more to come. So a business analyst can use their favorite tools. They don't have to learn something different for JSON in order to see their data in Capella Columnar and do the analysis and the charting and the, creating the dashboards and things with those tools. Under the hood, Capella Columnar has JDBC and ODBC connectivity that allows those tools to talk to it via a sort of a SQL 92 compatible query mode that we offer. The BI tools then see a Capella Columnar database as a network of first normal form tables, even though that's not really what it is if you log underneath. So how does that work? So one of the features of Capella Columnar is support for something we call tabular views. And so when you want to create something you want an analyst to see from your data, you can write a tabular view description in SQL++ that essentially shows the data. And I'll show you an example of this on the next slide. Shows the data in tabular form. They get to put on relational glasses to see their JSON data. The signatures of the views, essentially the definitions of those views, sort of explain how the BI tools will see the data as SQL data, and then constraints on the views, and I'll sort of show you an example of that, sort of hook things together so that they can use their drag and drop join builders and things in those tools. The underlying data, however, is still your JSON document data. We're not materializing those tools. We're not ETLing that data. Don't have to wait for any of that. You're actually seeing your current data, your JSON data, as though it were relational, using your BI tool so you can see what's going on right now with these relational glasses. So this is sort of an example. Suppose you have customers. And so here we've got an example of a customer, which in JSON, has these fields, and the address might be a nested object. We have orders, and in JSON, orders have line items inside them because that's kind of where line items belong. Shopping carts look similar in JSON. And so an order has some top-level fields, but it also has an array of items that comprise the order. Then we have information maybe about products that turns out to be kind of flat, so there's not much of an issue here. And so what we want to do is put on our JSON to relational glasses, our tabular glasses, and see this data relationally. And so tabular views basically allow you to define sort of these virtual tables that says, okay, here's how the customer information is going to look. So we can kind of flatten out the address. So we have just flat fields. So this is a nice first normal form relational table. We can sort of show the orders as two tables, even though it's really one collection of JSON documents, the order part and the line item part. where the order ID sort of connects you back to the order information. And then, the items are inside the orders. Sorry, this is yeah, exactly. And we have the items as well down here, which are the products that are available, which are being referred to from the items. So here we have like a network, a traditional network of what look like relational tables. They're really just tabular views of this data. And now the relational tools can run their SQL queries against this view. So that's in a nutshell what tabular views are, and I won't sort of go under the hood and explain exactly how that works, but we basically sort of compile your SQL queries against this into your SQL++ queries against this and get you your answer in real time and present it to the BI tool in this form. So that's one feature that Capella Columnar offers. Under the hood, when you ask your questions and you've got a lot of data, you want your answers quickly. How does that work? The answer is massively parallel processing. Is what it's called. It massively sounds, a little bit, glorious or whatever, but MPP is kind of what people use as the term for this. So I'll use that term as well. So sort of the more academic term for this would be partitioned parallelism. So the idea is you have a bunch of nodes in a cluster that are working together to compute the answer to a query. So let's call those compute units. And when you run a query in Capella Columnar, all the compute units in your cluster are enlisted to process your query against partitions of your data. And I'll show you a picture of that in a little while as well. Things like projections and selections are happening in parallel at all the nodes on your data, right? So that if you need to scale, and we'll talk about that too, you can add more nodes. And then things like joins and sorting and grouped aggregation and window query processing, all those things are parallelized. And so you might ask, well, how are you doing that? Well, the answer is the relational community spent 5 decades, 2 or 3 of which were on how do you do data warehouses and parallel query processing. And so we use that same best of breed approach generalized to JSON to do processing in parallel of your JSON data. We do not assume that data fits in memory, so we use also the same best of breed techniques developed over decades for having the sort of things get written temporarily and read back and so on to spill so on when you have data that is large and where that's necessary. And so as a result, we essentially give you linear performance scaling for complex queries. If you don't like how fast your query is running, just throw a little bit more hardware at it in terms of nodes, make your cluster bigger, and we'll get your time down. Also, we have columnar storage, and we'll talk more about that, where essentially we only read what you need. So if you're doing analysis, you've got 100 columns in your collection, or some of which are nested, et cetera. You're only accessing a few of them for some piece of analysis that you're doing. We'll only read those columns, and I'll show you sort of a picture that explains how we do that. That's something that the relational community has done. This is new for the JSON community. And then partition parallelism is also used, like we also do parallel processing when you're querying external data. So basically, and I'll take you through a picture of this as well, all the compute units get a share of the files to be processed that are in your external object store. And we even have some optimizations that we can do to limit how many files have to get read when you're running queries. So sort of read what you need is kind of one of the main themes here under the hood for efficiency. All right, so let me give you a picture just to get a sense, convey a sense of how massively parallel processing works. So today happens to be Friday. And so that means that, beer is important later today. And so we might have a database that has information about, breweries and the beers, different kinds of beers they have. And so an important question for deciding on, what to do later today might be, tell me for each brewery, how many beers does that brewery have? How many different kinds of beer? So we could, might want to run this query, select the brewery ID and the count of the number of beers from the beers collection, and group that by brewery ID. Want to run that in parallel because, end of the day is coming and we want the answer fast. So here's an example, sort of toy size, so it fits on a slide. We've got 3 partitions of our data, and so they're going to get processed. Let's assume that we have 3 cluster nodes that are processing that data, and so this is our data kind of at rest, right? So we've got, sort of the brewery ID 3 has Dubai Duvel as one of the beer kinds, and Saison is another beer kind. Brewery 2 has Pilsner as one of its beer kinds. And so you see there's a bunch of different kinds of beer and associated with the breweries that offer that kind of beer. And so the question is, how can we answer that query in parallel? So what we do is what sort of most data warehouse kinds of systems do to parallel process this kind of query. So basically, we start by having each node, each compute node. So we've got 3 compute nodes working on this that are assigned to help with this process, basically doing a local aggregation. So for each brewery ID, how many beers do they have locally, right? So at this node, we've got like brewery 3 has 2 beers and brewery 2 has 1 beer. And similarly, at this node, we see, sort of similar information. Brewery 1 has 2, and brewery 2 has 1. And at this node, brewery 2 has 1, brewery 1 has 1, and brewery 3 has 1. So these nodes locally aggregate. And so now we know, like, for a given brewery ID, how many beers does it have on that node? But we want to know for the brewery IDs overall. So what happens then is the data gets repartitioned in such a way that all the data from one brewery ID will be on one node. Okay, and so here we see that all the brewery ID 2s got routed here to this node to deal with going forward. And so, basically this node said, hey, brewery 2's got 1 beer. This node said the same thing, and so did this. And so we get that information here. And likewise, brewery ID 3's information landed here. Brewery ID's 1's information landed here. And so now those nodes can do the math and add up to compute the final total. Right. So now we know, for each of these breweries, how many beers they have, and that information is now distributed over our system. So we've computed that answer in parallel. So that's an example of a parallel algorithm for doing like the kinds of analyses that you might be wanting to do over your data. This is what we do under the hood for doing parallel handling of aggregation queries. That just gives you a sense of what we mean when we say MPP and how it scales. And you can imagine if you had a lot of beers and a lot of breweries and a lot of nodes, how that would scale up as you size that system up. All right. One of the other really important things in the cloud is to have storage compute separation. So once upon a time, the answer to how should data warehouses be architected was shared nothing. You get a cluster, and each cluster has some of the data stored on it. As we move to the cloud, you want your data and your compute to be separated so that your data can, sort of rest forever in your system, and you can fire up compute as needed. And so the storage compute separation that Capella Columnar is based on allows us to have a more serverless kind of pay-as-you-go analytics. You can, fire up and use Capella Columnar for a while, and you can turn it off and not have to pay for the compute. The compute costs, just pay for the storage sitting at rest. So how does this work? So data is owned and managed by the Capella Columnar service, the storage layer of that service. The bits at rest are housed and managed in object storage. So in our first offering, I'll talk more about the kind of the roadmap there, but that object storage was S3. Again, Google is right around the corner. The in-use collections and indexes are cached on the compute nodes in NVRAM. And that caching is sort of eager on reads, but right through on updates, so that the bits at rest, the facts are stored in your object store. The collections are over-partitioned so that we can assign a variable number of compute nodes and then give them each responsibility for a set of the partitions of the storage. So this allows reassigning, and I'll show a picture of this in a minute, of data to compute nodes. So each compute unit is solely responsible, sort of temporary shared nothing, for its assigned partitions. But you can scale your service up and down based on your performance goals. And again, I'll demo this in PowerPoint mode in just a second. So basically, it's sort of a shared nothing, shared disk hybrid architecture. So it's not like any node can operate on any data, but at the moment, these nodes in your cluster are responsible for these partitions of your storage. So what does that look like, as a cartoon, if you will, and how is that beneficial? So here we've got some data, just 2 nodes. And suppose we have 1 node at the moment. Again, this is all just to sort of get the concepts across. And so we've got, let's say, 8 storage partitions. Again, this is just sort of conceptual. The real numbers are much bigger. So we've got sitting in our object store, there are 8 partitions of our data. And, maybe we've got one node, and it's assigned to be responsible for all of those partitions. And, we're running a query and it's taking 2 seconds, and we're like, well, that's not good. I need my answer faster than that. I need it in 1 second. So how do we solve that problem? What you can do is you can scale up your Capella columnar instance. Now we've got 2 nodes. They each are responsible for half of the stored data, and they're going to run in parallel, which we just talked about. And so now your query, rather than taking 2 seconds, is going to take 1 second, because each node will be computing its part of the answer to the query in parallel. So the storage compute separation allows you to adjust your cluster size to your performance requirements nicely. And it doesn't take very long, because it's basically just reassigning who's in charge of what. We're actually not having to shuffle the data around the universe to do that kind of repartitioning and scaling up. Let me talk a little bit further under the hood about what that storage compute separation looks like. Again, this sort of hybrid shared disk, shared nothing approach. So suppose we have 2 nodes, or actually n nodes in this picture now. Each of those nodes is responsible for some set of partitions of your storage. What does that look like? So a partition, basically we take your data and its indexes, and we partition that into a bunch of storage partitions, and which piece of data goes where is based on hashing on the primary key of your collection. So maybe we've got information about users, and so the user ID is the primary key, and so we're going to hash the data based on the user ID. So a given user will be in exactly one of those storage partitions. So then the data was going to live in what we call a primary index. So the primary index associates the primary key with the data records. And so here's our primary index, sort of showing your data. The red stuff is like data that's just come in. It's in a memory component of what's called a log structured merge tree. And then when that memory component fills, it gets written to disk. And so now you have a disk component, and we'll start filling a new memory component. And then when we get a few disk components and we want to reduce the number of those, we'll merge them together into bigger disk components. All that stuff is happening kind of behind the scenes under the hood. And then we use a technique called Bloom filters to help avoid, as you're searching through your LSM index structure, which is essentially a little series of B trees, to avoid having you look in components that might not have your data. So this is kind of the under the hood view of your primary index. And then you may want to index your data, based on name, because your application is looking things up based on username, or on zip code because you wanted to do analytics over the zip code, and you want to do it for a specific zip code or a small range of zip codes. So you might build secondary indexes. And so the secondary indexes for the data in a storage partition are local to that storage partition, meaning that all the data that's in this partition is here in the primary index, and then its secondary index entries, which say for the secondary key, here's the primary key. Those also live together in that same storage partition. And then so record updates turn out to always be local in this architecture. So that's just a little bit of information about kind of what's under the hood with respect to how data sits in distributed storage and how it's associated with compute nodes, as you saw in the previous slide. What about columnar storage? So those of you who have been in the relational world, you're aware of, sort of the columnar versus row data. Kind of in the early days, data was stored as rows. And then when people wanted to start doing analytics, where you had many columns and they only wanted to access a few columns, you would want things organized by column rather than by row. So this is old news in the relational world, but it's new in the JSON world. So JSON databases have traditionally been row-based. The Couchbase one for operational is, for good reasons, row-based. Couchbase Analytics was row-based, but Couchbase Columnar, hence the name, actually sort of takes and turns your JSON into sort of a generalization of columns. Some of the challenges in doing that are, dealing with JSON data, are the data bloat that you get because data is in JSON self-describing. And so the schema sort of is inferred from the data. The heterogeneity. So fields in a relational database, once a decimal, always a decimal. In the JSON world, a given field can be of several different data types potentially. It could be a string or integer, so this kind of heterogeneity that can occur in your data naturally or in your data as it's evolving is something that's a reality in JSON, but not a problem in the relational world. So it's a challenge for doing columnar storage for JSON. And then the fact that the data can be nested, it's not just flat columns, rows and columns. It's now, one of the column values can be itself an object or an array of objects. That also requires work to deal with that in a columnar kind of way. So what do we do in Columnar? So one of the things that is done in Columnar is that as the data is coming in and sort of flowing into that LSM structure you saw on the previous slide, we actually look at the data and we separate the data into a schema part and the data part. And so if most of your data looks the same, it'll be described by the same little schema part. And so we've separated those bits. So we're able to sort of get relational storage efficiency, from JSON data by separating schema from data kind of on the fly based on the data coming in and us sniffing that data. The data is then stored in an efficient binary format. I'll talk a little bit more about that on the next slide. And this is accomplished technically by exploiting the LSM component lifecycle. So let me go back one slide. Basically, data comes into memory. When that data is flushed from memory to disk, the schema is separated from the data, and the schema is associated with the data in a way that I'll show you next. But before I do that, let me also talk about sort of the storage of JSON collections in a columnar kind of way rather than in a row kind of way. So we generalize the notion of column to deal with the nesting heterogeneity. So we store things in a JSON version of Columnar, which then allows us to compress the data. We've taken away the schema and also use, sort of data compression techniques, run length encoding, things like that, to encode the columns to reduce how much space they take, and therefore how much I/O is being performed when you're reading that data. We offer secondary indexes to further accelerate query processing. And I just want to emphasize, this is a data greater than memory system, so there's no requirement for things to fit in memory for this stuff. And all of the columnar data, whether it's like being created in Columnar or coming in from one of those external sources, benefit from this columnarization, if you will, of the data. So let's just double click on that a little bit, separating schemas from data. So there's, sort of some cartoon JSON data where we have a couple of people with phone numbers, and the phone numbers, there might be a type of phone associated with that. It shows a little bit about the heterogeneity of JSON data, right? So we've got, this person's phone, you just have the number. This person has two different phones, so we have a type and we have the number for that type. So that gets put into your LSM storage. And when it's put in, as I mentioned, we separate the schema from the data. And so the data is being observed, and there's a schema which describes the data that we've seen so far that's getting updated as we see new data. So at this point, what we've seen is that the data is JSON objects. And, one of the columns, which turns out to be the name column here, is of type string. And so we've separated the fact that we've got an object with a field name or a key name, if you will, and a type of string from the data, which is John and Max and those two records. So the data basically has the data values, but the schema knows, what they're called and, where they are, column 0, essentially. And then we also see we've got this phone array. So we know that we have an array. It's an array of objects, and the objects have a collection of fields, including a type field here and a number field here. And, this is a string, and this is also a string, what we've seen in this simple example. And then the data is stored separately. It turns out that John didn't have a type field, and so we have a null there. And then missing information, but we have the number field. and likewise for the other fields. All right, so basically we do this separation of schema from data, and now once we have things sort of laid out in this columnar way, you can kind of look at this and go, oh, I see how you could do some compression on that, right? And so we do that kind of compression under the hood then of that data to make that the space occupied by that column's binary data even smaller. So that's just a little sort of high-level view of how we sort of deal with the separation of schema from data and the benefits that that gives us in terms of now being able to go after the data, only the columns that we need, and to have their data types separated from the data values. All right, so, and again, sort of where do we put this stuff? Well, the data columns are stored in these LSM components, and at the top of each LSM component, there's a little piece, which is got the schema information for all the data in that component, as opposed to each object carrying its own schema information. All right, so let's move on to another aspect of the under-the-hood technologies of Couchbase Columnar, which is the cost-based optimizer. And again, what we've done is to say, okay, the database community has been working for 50 plus years to optimize queries. That is great knowledge. We're going to stand on the shoulders of giants and apply the same techniques generalized to deal with JSON data. And one of the current state-of-the-art ways of dealing with query optimization, for reasons that I'll explain in a second, is based on samples. So the Columnar CBO, cost-based optimizer, works using samples of your collections. So periodically, you will ask the system to sample a collection, and it'll create like a little stored sample of your large collection. And it'll have stored samples for each of your large collections. While that sampling is being done, it'll also count how many objects it's seeing. And so the optimizer will have access to little samples of each of your collections and information about how big the samples are and how big the collections were. And so we're going to see that having that information allows us to do a really good job of estimating like how big the results are going to be when we apply complex predicates like likes or arbitrary expressions or functions, or if there's data correlations. Again, I'll sort of show you that in an example in just a second. So the optimizer actually uses those little samples at query compile time to figure out how to build a good query plan to make your query run fast. It does that by running little queries on these little samples and using what it learns by doing that to determine a good query plan. And some of the things it's trying to decide is, should I use this index or not? Which order should I do my joins in? Hash join or nested loop join, how should I do the join? If I'm doing aggregation, should I use a sort-based or a hash-based approach? So these kinds of decisions needed to be guided by cost estimates, which need cardinality information, which comes from this sampling technology under the hood. So the bottom line is that the way we do this is based on samples, state-of-the-art, and it's more powerful than trying to do things based on histograms, which have a much tougher problem when you're dealing with things like likes or function calls and so on, or multiple attributes that might be correlated. So let's just take an example to illustrate that. So again, we're basically, leveraging knowledge from decades of relational expertise and bringing that to bear to have a state-of-the-art sort of JSON data analytics capability. So here's an example of a query against that sort of sample data we saw earlier. I want to look at my customers and my orders. I want to join them. So I want to look at the orders for customer ID. I'm interested in doing that where the customer has a city that satisfies this like predicate, and where one of the items in the order is expensive in terms of how much quantity times price is for that item. All right, so it's kind of a complicated query. And then in the end, I want to order by order date, and I want to do a limit 100 because I just want to get an initial idea of what this looks like. So there's my query, and I've got my customers collection and my orders collection, and they're kind of shown in this, sort of LSM tree kind of picture. What goes on under the hood? Excuse me. So cost-based optimizer's job is to figure out, how should I run this query? And so what it does to get that information using samples is that it takes sort of the customer part of the query, and it runs a little query on the customer sample and asks the question part of the question, I should say, that's customer related. So the optimizer, to optimize this query, one of the questions it will ask to get some information that it can use to do cost estimation is, how many customers in my sample satisfy the address.city is like %MA predicate, right? And so now, rather than having to try to figure out how to deal with likes and histograms, which is a nightmare, basically it just runs that query on the sample, and then it can upscale the result. Okay, how many things in the sample satisfy that predicate? And I know how big the sample is, and I know how big the collection is. Now I can estimate how many customers will satisfy that predicate. And then likewise, there's a part of this predicate, which is kind of complicated because it's JSON and there's nested data. I'm interested in finding this overall answer only for the orders that have items that quantity times price is greater than 500. Good luck with histograms doing that. But with sampling, what the system can do, what the CBO optimizer for Capella Columnar does, is it says, okay, how many things in my sample, in my order sample, satisfy this predicate? So I'll just ask the sample, how many items do you have that satisfies this expense predicate, right? And so then now it will know how many orders satisfy that predicate, and then it can proceed to use that in the bigger picture to overall optimize that query. So that's kind of what's happening. That's interesting and novel under the hood in terms of the Capella technology for cost-based query optimization. What else have we got? Well, we have external collections, as I mentioned, and there are multiple ways that you can access data in external object storage. So again, I'm going to use S3 as an example, but we support other kinds of object storage here. But S3, is sort of one of the favorites out there, so it's always fun to use that as an example. So what we offer is the ability to create external collections. So you can basically, point us at files in your S3 object store in such a way that they look to you when you're looking at them with your glasses from Capella Columnar on as another collection of data. Looks just like an internal collection. You query it just like it was an internal collection, but we run the query differently, obviously, because it's not. We support multiple file formats. So, your favorite file formats are supportable for your external data. JSON, CSV, TSV, Parquet, Avro, paths, and filters are available as a technology, and I'll sort of explain this on the next slide, to indicate which folders to include or exclude. So you point us at your object storage when you're creating an external collection, and you can also give some additional information that says, like, where within your object store, like, are the files that relate to this external collection to be found, and how are they organized? And the how are they organized part is about something we call dynamic paths, which allow you to turn your folder structures in your object store into queryable data. And I'll sort of illustrate that on the next slide. And then we have DML support, SQL++ support, so that you can read data and write data to and from external collections. So there's a copy from statement that allows you to load data from your object store into a standalone collection, basically to snapshot that data into managed storage in Capella Columnar, and then you can index it and sort of work with it from there. So that's sort of a way you can import that data once or periodically. You can also run a query and create a collection based on querying your external data. It might get you a small snapshot of that data that you want to do some slicing and dicing with, for a few hours today, and manipulate locally rather than having to go to external storage for it. And then we also have a copy to statement that goes the other way, so that you can write data back to an external collection, and you can actually structure it kind of in a way that takes advantage of this sort of optimization that I'll tell you about if you want to. So again, what this does sort of in a nutshell is it makes your external data look as though it were stored internally, and you can query it together with your internal data. So here's just an example of that. So suppose we have, sitting in, let's say, S3, we've got a collection of files. We have a directory-like structure. It's not really directories, right? But we sort of a naming structure that says that there's like a reviews folder. Inside that, there's something which has a year as its name. Inside that, there's a subfolder, again, logically, which has a quarter indicator as its name. Under that, we have things by month, and under that, we have our data files. So maybe that's how you've got your external storage organized. So now if you want to create a collection that sort of views that as a JSON collection. How does that work? Well, you create an external collection, you give it a name, you say, sort of information about what's the object, sort of container, and where's a link to sort of get to your S3. The link is the credentials. And then you tell it kind of, starting from there, how do you find the data? Well, the path to the data that I'm interested in is of the form reviews, and then, and then this magic here. So everything under reviews, is stuff we're interested in. And then this path description sort of describes the logical structure and how it relates semantically to the way I think about my data. So the next level of foldering, if you will, is the year. It's an integer. The next level of foldering is the quarter, and the next level of foldering is the month, right? And so this basically sort of defines the structure to Columnar so that it can exploit that structure when processing queries. So we've got our data. Now we've got all of this data. Looks like it's simply in a collection called, my external collection. And we can now query that. So we've got a user, and the user wants to know, hey, I want to select, all the stuff from my external collection M, where the year is 2019 and the quarter is Q1 or the quarter is Q4. And so we really want to just, we're really interested in just the data that's kind of highlighted in red down here. That's what the query is targeting. We don't really want to read the other stuff. And so it turns out with this sort of path magic, you don't have to. How does that work? Well, when that query is compiled, we'll take that query, and Columnar will go and sort of ask the external storage to tell it the metadata, basically what's the structure, the reviews, et cetera. What's the structure you've got? Like what data do you have out there? What files do you have? And so it will basically go out and sort of get a list of the files that are stored kind of at that external location. And once it knows that, it can apply filtering that it gets from this path and combines with this query to only deal with the stuff we care about, right? So we really only care about the red stuff down here, which turns into kind of this set of paths, right? These are the files that we really would like to query in order to answer this user's business question, right? Or, the show me the data question. And so that filtering works because basically this path definition sort of makes year, quarter, and month look like they are attributes of the data. And it allows then the system to say, okay, I'm restricting my attention to these attributes, and so I only have to read the files that might be relevant. And so that filter basically allows us to pare down and not read all the files, just to read those files. And then that list of files basically gets divided up, massively parallel processing, into a set of partitions to then be processed in parallel, right? So that then the query processor will read those things in parallel, apply the rest of the criteria if there had been any, then parallel do the aggregation or whatever in parallel if that had been a more complicated query. So that's kind of a little bit about what's under the hood for external data. So that was data coming in. What about data going out? Well, just sort of very quickly, you can do that too. So you can actually take data and push it out to your favorite data lake or your external object store. So this is an example of a copy to query in Columnar. Suppose you wanted to, you've got some reviews data, and suppose you have an internal collection. You've got a collection of data sitting in Columnar called My Reviews. And now you want to stick it in S3. You want to share it in S3 for whatever reason. And so you can write that data out to S3 by using this kind of a copy to query. So here we've got our reviews with our information like what's the review and what's the rating and what's the year, quarter, and month associated with that review. Our copy to query can query our internal collection, our stored collection in Capella Columnar. We can copy the information from the result of that query out to our S3 storage or our other object store, specifying, sort of the path information that we want. And we can actually do this in a way, I'm not going to go through this in detail, but that kind of recreates that partitioning that we talked about in the previous example. So you can actually, as you write the data out, you can partition it into this kind of a structure so that, sort of the stuff for Q1 2018 appears here, and the stuff for, sort of October of, Q4 2020 appears here, and so on. So this sort of round trippable structure is also supported in Columnar, so that then if you wanted to come back and query this data as an external collection, you'd be able to have benefits of all those optimizations that I talked about. And then how does data come in other than either being put there explicitly or being external? Well, the answer is we support streaming data ingestion. And we have sort of two kinds of streaming support right now. DCP, Data Change Protocol, which is sort of Couchbase streaming from Couchbase on-prem or Couchbase Capella operational. We also have Kafka streaming. So if your enterprise has, it's various data sources, your relational databases, your other document stores, connected via Kafka to your enterprise universe, you can stream your data using that Kafka infrastructure into Capella Columnar. And then we also support standalone collections, so you can just manage your data in Capella Columnar. But a key way of data getting there, sort of the most common path is, one of the most common paths is we expect it to either be copied into, as we talked about, from external storage, or streamed in real time, all the time, so that you can look at your data as it's changing, as it is in your operational data store. So if you're streaming data via DCP, you're streaming Couchbase data, it could be coming from the data service in Capella Columnar, in operational Capella, Couchbase Capella, or Couchbase Server. And that's based on technology we've had for a while called remote links and Couchbase Analytics. Basically what Columnar is doing, it's a listener to this data change stream, and it's keeping your copy of that data in Columnar, which is separate from where it is in your object or in your sort of operational data store. It's basically dealing with the changes and applying those changes to its copy. And so as a result, you have a near-time shadow of the data. So that data might be your Capella operational data. It might be MongoDB data that's being Kafka'd into Capella Columnar. You're getting a real-time snapshot, basically, of that data all the time, real-time view of that data, and you can run your queries on the data. As it's happening over there, you're querying it over here on, on separate, sort of storage and compute infrastructure. You can do this, via data change protocol, as I said, for Couchbase data, and then for other external data like Mongo data, or very soon DynamoDB data, or your favorite relational database data. That streaming is coming in via Kafka. It's kind of the, playing the DCP-like role, but for more general for your enterprise. So it's coming from your other sources. Again, we support several relational databases today, more on the horizon. MongoDB today, DynamoDB very soon, Cassandra's, a gleam in our eye for sure, based on Kafka connectors for the remote system. So Kafka is essentially playing an enterprise DCP kind of role here. And again, the result is a near real-time shadow of your source data. So sort of again, sort of a cartoon level picture, the data can land in and be managed in Columnar, either coming from DCP streams, Kafka streams, or just put there, via inserts, upserts, deletes, and so on, talking to Capella Columnar. DCP is dealing with server, Couchbase server data, and Capella operational data, and your other data sources would be coming in via Kafka, and here is your Columnar instance. So streaming data ingestion is one of the big ways that the data comes in. And again, one of the other important things to remember, if you go back and sort of picture that very initial IT slide, is that once your data, it's not just that you're using Columnar to analyze data from Couchbase Server. It's like this data is coming from a variety of different sources. It's brought together in Columnar, and you can do cross-analyses, right? So your queries can be querying data, some of which came from one of your on-prem instances, some of which came from your operational Capella in the cloud instance, some of which came from your relational data, some of which is in MongoDB, but it's all together in your columnar collections, and so you can query across it and get sort of cross-source insights very easily using Capella Columnar. All right, so that brings us pretty close to the end of the presentation. So once again, Capella Columnar is this new service. As we were private previewing starting at the very end of 2023, and the service just launched a couple of months ago. So it's a pretty new capability that you can get from Couchbase Cloud. And so it's very interesting because of the things that I've described to you. It's ever so much more than just columnar storage. So you might look at the name and go, oh, columnar storage, that's cool, but it is much more than that, right? So with Capella Columnar as this cloud DBaaS offering for JSON analytics, you get SQL++, which is, basically bringing your SQL skills to bear on JSON data. So that's easy to learn if you know SQL. And it's under the hood doing MPP-based query evaluation. So you're able to do analytics over very large volumes of data, applying parallelization, right? And you can scale out if you want to get faster queries. Under the hood, there's like native storage for JSON analytics. That's Columnar in its base. This storage compute separation that I talked about for allowing you to do that scaling, and also you can sort of turn off the compute part of your Columnar cluster when you're not using it, so the data will remain. You can come back and turn it back on and use it again. So it's you're not paying for compute all the time when you're not using it. You don't have to do that. Under the hood, state-of-the-art cost-based query optimization based on sampling, continuous data ingestion we just talked about, optimized access to external storage, talked about how the structure of the data there can be used to restrict the amount of data that has to get read, and then integration with BI tools, right? So I sort of went back up the stack from what we talked about. So all of that is what you get with Capella Columnar. And so I encourage you to give it a try. It can hopefully, be helpful in getting your enterprise the kind of insights it needs quickly without having to, sort of decide on relational schemas and do ETL and sort of all that kind of heavy lifting. So the data can come as it is and have all those technologies applied to solving your business problems quickly. So just kind of a last stop here. Let's just take a quick look at what Capella Columnar looked like on my Mac last night when I was doing a screenshot for this. So as you look at your data, you can enter your queries here. You can look at your query results here in JSON form or tabular form. You can chart it. You can look at your query plans, either graphically or textually. And so this is kind of where you can sit and work on and edit your queries and, sort of get your insights, before you maybe get things going with your application, or you can just use this as your workbench for doing analytics. On the left-hand side, you kind of see what your databases are. So I've got a bunch of different databases here. One of them is called Shop-A-Lot, which is a database about shopping that I used to use when I was teaching big data in my previous faculty life. And within that Shop-A-Lot database, I've got what's a scope, kind of like a schema and relational, called Web Store. And within that, I've got various collections like orders, products, remote users, and so on. And if you click on one of your collections, the system will sort of show you the inferred schema for that. So over here, you kind of get an overview of your data. Here's where you query it. Here's where you see the results. And on the right-hand side, you can either click on history and you can see your query history and go back and forth and edit your queries and so on. Or we have this cool feature called IQ. So the IQ feature for Capella Columnar can be used to sort of help you write your queries. So here's an example, sort of I asked it to, hey, think about the orders, users, and products, and, help me by showing me the most recently placed order across all users and the name of the user who placed it. So that's my English question for my data. And so I asked that question, and what came back when IQ responded was it said, okay, here's a query. And so it basically wrote the SQL Plus query for me. And now my job as a responsible user of LLM technology is to remember that LLMs are not perfect. And so I will look at that query and go, yep, that was what I was thinking. And now I can run that query, or I can copy it and put it in my application or whatever. And so when I ran that particular query, when I clicked run, it moved my query over here. And it ran the query for me, and it showed me my result, right? So I got back the username, and I got back the orders that I wanted. So that, in a nutshell, is what I wanted to tell you today about Capella Columnar. And so I encourage you to, take a look at it, give it a try. If you're interested in learning more, so that you can shoot me an email or shoot an email to my colleague, Till Westman, who helped create this presentation. And so thank you for listening. And I will sign out here and let you get in touch with us if you're interested, or just go and check out at couchbase.com the information about Capella Columnar. Thanks.